This is example 6-4, flow through an elbow. So you can see here kind of a pipe that's at a 90-degree angle, and then there's a nozzle where the water can rush out. And we're told that we have some kind of connection here at A, and we're asked to find out what the horizontal and vertical force components are and what the moment is to hold this pipe, bend this elbow here in place. And we're given what the velocity is of the water coming in, and then we're also given some dimensions. So if we're looking for forces, then of course we have to draw ourselves a free body diagram. In our case, the control volume that we're going to choose is just the water inside of this this elbow here from surface at here. Maybe we'll call that B, all the way down to A. So let's see how badly I can draw this. So let's say we have a little flat part, opens up. As I said, drawing not always my strong suit here. Like this, maybe we'll have it go down just a little bit, and then it starts turning. Something like that. Fortunately, accuracy of my drawing doesn't really impact the result, right? So we say we have B up here, A down there. We'll have some forces. We'll have the horizontal and vertical components. So let's say you call this AX. And we'll have a vertical component AY. And we also have a moment. So that's our moment. We'll call that MA. Now the other part that we'll have is we have a closed pipe here, right? So there's going to be a pressure at A, which means that we have to take that into account. So we have our nice little distributed load PA, and of course we can create a resultant force of that and call that FA. All right, and once we have all those, then of course if we want to find the forces here to create the balance of forces, then we'll have to use the linear momentum equation, and then for the moment we'll have to use the angular momentum equation. But before we can do that, we have to go in and find a whole bunch of details. Where are we going to start? Let's start with the flow rate, right? That's a pretty standard one. So I'll say volumetric flow rate. Now, flow with a V, that doesn't get us very far. Flow rate is Q, and that we're given what the velocity and the diameter is at A, so we'll just say that is VA times AA. VA is 3 meters per second, and then the area is pi over 4 times the diameter there is 80 millimeters, so 0.08 meters squared, and that gives us 0.0150,796 cubic meters per second. So that'd be the flow rate. What else do we know? What else do we need to know? Well, we'll need to know the velocities at the control surfaces. What are control surfaces here, right? So we'll have a control surface right there at A. We know the velocity there. Our other control surfaces right here at B. So we don't know that one yet. So let's figure out what VB is. Well, for that, we can just use continuity. From continuity, well, we know that VA is not equal to VA times AA is equal to VB times AB. That means my VB, that's what we're trying to solve for, right? So we have to have VA times AA over AB, so we can say that would be AA over AB times VA. No, this is going to be pi over 4 d squared. The pi 4's cancel out, and we can pull the square around the 2, so we'd have dA over dB squared times VA. In our case, we had 80 and 40, so that's a factor of 2, so we'll have a factor of 4. But let's write it out. Right? So that'd be 80 millimeters at A and 40 millimeters at B. Don't need to change the units here because they're just going to cancel out anyway. And then my velocity at A was 3 meters per second. So that means 12 meters per second would be my velocity at B. Okay, what else do we need to know? We have the pressure, PA. We're not given the pressure. At PB, of course, we know that PB is equal 0 because we're at the surface, at the atmosphere. But for A, we're not so lucky, right? So we'll have to figure out what that is. So we'll write Bernoulli. So let's say Bernoulli and we'll say that these height difference here, that 300 millimeters, we'll call that negligible. We'll throw that out. Say with negligible elevation change. And point B at atmosphere. All right, then we get PA over gamma. That's what we're looking for. PA over gamma. The velocity of A we know, so VA squared over 2G. We're saying this is 0. PB we said is 0. We know what VB is, we just calculated it, and this is 0 as well. So if we then want to solve for PA, right, then we'd bring the VA over, multiply by gamma. So we'd have PA would be gamma over 2G times VB squared minus VA. Right, let's bring it over, get the two A's, the velocities together, and that. Of course, gamma over G is rho, so we can say that be rho divided by 2 of VB squared minus VA squared. And then what we do get for values, well, we have water, so it's 1,000 kilograms per cubic meter divided by 2. And then VB, let's make that a square bracket here. So we have VB was 12 meters per second, and not plus but minus. VA was 3 meters per second. That squared. Plug those numbers in. We get 67,500 pascals, or let's just write it as Newton per square meters, because in the end we want to get the force, right? We want to find this force here. So to do that, we now have the pressure. We know this is a circular cross section, so we can say FA is equal to PA times AA. So that'd be 67,500 Newton per meter squared times pi over 4, 80 millimeters, right? Yeah, 80 millimeters. So 0.08 meters, and that's squared, and that gives me 339.292 Newton. All right, is there anything else that we need to figure out? Let's see. Have our velocities, we have our force here, so I think we're good. So we can start looking for AX, AY, and MA. So for AX and AY, we'll need our linear momentum equation. Linear momentum equation. All right, that tells us that sum of forces is equal to the time rate of change integral over the control volume of V times rho dV, right? So that change the volume plus the integral over the control surfaces of V times rho times V dotted with dA. All right, so we can do our usual set of conditions, right? We can say we have steady flow. We have uniform velocity profiles. Velocity. Velocity. That doesn't look good. Let's erase that word. There we go. Velocity profiles. And we also have an ideal fluid. Remember, ideal fluid is incompressible and inviscid. In our case, the incompressible part is important, right? That means if the flow is steady and it's incompressible, then there's no time rate of change. That's equal to 0. So we can say sum of forces is equal to 0. Not equal to 0. Oh, 0 plus, I guess we can say. And then the rest back here just turns into a sum. Right, so that would be the sum of velocity times rho times the velocity dotted with the area. All right, now for our specific case, if we want to write that sum, right, we know we have a velocity at A, and then we have to think about that V times A, is that positive or negative? At A, my area vector is pointing out and my velocity vector is pointing in, so it's negative. So I would get, where are we? That times, so VA times rho, and then minus AA times VA, and then plus VB, that's my other control surface, times rho, and then let's see. Here my A is going to be pointing, of course, out of the control volume, and my flow is also in that direction, so I get positive. So it's just AB times VB. All right, so that's now our general equation in the for our linear momentum equation. Actually, we can simplify that just a little bit more. That's right. It'd be minus VA times rho, and of course AA times VA is just Q. So I'll just write times Q plus VB vector rho times Q. So shortened up a little bit. And now to get AX and AY, we just have to write the two component equations, right? This is a vector equation, so we use component vectors, we'll have two equations. We'll have the sum of forces in the x direction is equal to, so we're giving our velocity in A. Now velocity in A, we need to have, we not put a coordinate system. Let's put a coordinate system. X and Y, so we know which direction X and Y are positive. And at A, the flow is going in, or going to the left. That means it's negative because X is pointing to the right. So we'll have, we already have a negative sign there. Negative VA times rho times Q. And then let's look at VB. Well, VB, we don't have any component in the x direction of our flow, so that'd be 0. Plus 0, so that's those two negatives cancel out, and we said that yeah, cancel out. So we say VA times rho times Q, and what is that equal to? Let's see what the forces are in the x direction. We have AX positive and then minus FA. So it'd be AX minus FA. So now all we have to do is solve for AX, just like we used to do in statics. AX is then going to be VA times rho times Q plus FA. All right, so that means our VA was 3 meters per second. We have water, so 1,000 kilograms per cubic meters. And then our flow rate was 0.0150796 meters cubed per second. Let's not forget our our FA, 339.292 Newton, or 384.5309 Newton, 384 Newton. So that'd be our component in the x direction. Then we can do the same in the y direction. So sum of forces in the y direction is equal to, we have minus VA. There's no component there and for the velocity at A, so we have 0 plus, right, we have plus VB. At B we have, all of it goes in the y direction, and it's the same as our positive y direction, so it's plus. So we'll be keeping on plus, it'd be VB times rho times Q. And then what do we have on the forces side? Let's see. The only thing that we have is AY. So is equal to AY is equal to, if you plug numbers in, VB was 12 meters per second. Rho was 1,000 kilograms per cubic meters, and Q was 0.0150796 meters cubed per second. And that is then 180.9557 Newton, or 181 Newton. If we round to 3 significant digits, where's our AY? There. All right, so that's now 2 out of the 3 unknowns. We had the 2 forces and the moment. So now let's do the moment. To do the moment, we of course need our momentum equation, our angular momentum equation. So let's put that in. Where is my angular momentum equation? All right, so let's say what do we have for our momentum equation? Yep, let's scroll all the way down. So if we say, we'll just use the simplified form just to save a little time here. So we can say for steady flow, same as we had before, right? Uniform velocity profiles. Velocity profiles. Ideal fluid. And if we're only interested in our two-dimensional system, right, then we get something where we can say the sum of moments is just equal to the sum of the moment arms times the velocity times rho times q. So if we do this as a moment about point A, all right, let's think about this. Go back to our free body diagram, right? Of course, we want to do it around A because if we do it anywhere else, then we get all these different forces that become that have moment arms. So let's just do it at A. So that means we need to find what the velocity is that has a moment arm, or maybe we'll call it velocity arm, I don't know. VA, the velocity goes straight to the point, right? So it's not going to have anything. B, however, has a moment arm. And that moment arm is 300 millimeters. So let's go all the way down. So that would mean sum of forces at MA is then going to be equal to, what do we have, right? So we said 0.3 meters times VA times rho times Q. Now let's figure out if it's positive or negative. So just like we did with moments in 2D, we can say it's turning counterclockwise, it's positive. In this case, if we hold at A and turn B, right, then we see it's clockwise, so it should be negative. So let's put a negative sign there. And of course, that's all equal to whatever moments we get from forces. So we chose A because we don't get any moments from forces, but we do have our moment here, right? So our MA. So that all is equal to MA. So MA is then equal to minus 0.3 meters times 12 meters per second times 1,000 kilograms per cubic meters times 0.01507996 cubic meters per second, or minus 54.2867 Newton meters, or minus 54.3 Newton meters. So with that, we have found all the forces and the moment that's acting kind of this connector here between the elbow and the pipe. And so if we knew we'd have this amount of water flowing through it, then we could now dimension how strong this connection has to be.